Okay, so let's continue our study of congruence with something called congruence classes. This will be section 2.1. All right, it is common in math that you have things that are different, but that you want to count as the same. And we do that often with congruences. For instance, if we're working with time, say mod 12, then 3 and 15, and for that matter 27, are all congruent. In fact, everything in this set, 3, 15, 27, and so on, all of these numbers are congruent, and we want to count in some sense as the same. And it's a huge idea in mathematics that goes in essentially every area of math, on and on, is to take all the things that you want to count as being the same, lump them together in a set, and call that set something like a congruence class. And then the set of things that are all equal, then you start working with that set as if it were a number in its own right. All right, here's the definition. The congruence class of A mod n, we're going to write with square brackets, is the set of numbers B that are congruent to A mod n. All right. Some people will call congruence class, they'll use the word residue class. So if you see that word, they just mean congruence class. And then some people will have an alternate notation for these square brackets. One of the most common is to put a bar over it. So if you see that notation, they might mean congruence class, though both of these words are sometimes used with other meanings, so you have to look at the context. We'll stick with the square bracket most of the time. And frankly, mathematicians, when they're just writing on their own papers or when things are well understood, they'll often leave out the square brackets altogether, and you'll have to tell from context what they mean. But we'll try to keep them in. I guess the first thing that we really want to emphasize is that these congruence classes are sets. It's not a number, it's a set. It's a collection of all the things that are congruent to A mod n. So, for example, if we work mod 12, then 3, the congruence class of 3 is just all the integers that are congruent to it mod 12. So that's a big list. Here's some of them. Negative 12, negative 9, 3, 15, 27, 39, 51, and keep adding 12 or subtracting 12 as long as you want. Now, one thing that's kind of new with these congruence classes is that you can write down something that looks ostensibly different. Like the congruence class of 15, again mod 12. And if you write this out, look what we get. If you start with 15 and start subtracting 12, you get back to 3 and so forth. Or if you add 12, you go to 27, 39, and you see that you get the exact same set. So that, in fact, the congruence class of 3 is identical to the congruence class of 15. And it's by this mechanic that we can say 3 is equal to 15. What we really mean is the congruence class of 3 is equal to the congruence class of 15. I suppose maybe it looks odd at first, but most of the time when mathematicians want to take two things that are not technically equal, want to make them equal, they do a construction like this. So when mathematicians say 3 o'clock is 15 o'clock, this is usually how it's done with this formalism of lumping everything together in one giant set. It looks awkward at first, but it's just actually super useful. And I guess I want to emphasize again that the fact that different numbers generate the same congruence class happens a lot, and you have to be careful. In fact, we're going to add a definition here on the representative of a congruence class. In general, we say A is a representative of the congruence class A with the square bracket. So, for example, 3 and 15 are representatives of the equivalence class of 3. And that's because the equivalence class of 3 is the equivalence class of 15. In fact, you can add any multiple of 12 to 3 and get a different representative. Okay, let's go to our first lemma that talks about the behavior of these congruence classes. Our first result tells us exactly when two equivalence classes are equal. And the result is they're equal exactly when their representatives are congruent. The next result is that two equivalence classes are either identical or they don't meet at all. In other words, they're disjoint. Remember, they're sets. They're the identical set or they're disjoint. Okay, next is that the entire set of integers is the disjoint union of the congruence classes. So if you put them all together, they give a partition of all the integers. All right, number 4, if you do something that looks like the division algorithm and subtract off a bunch of multiples of n, then what counts as the remainder won't change the congruence class. All right. So divide a by n, and a is congruent to r. Number 5. There are exactly n congruence classes in Z, with mod n, of course, and you can even list them out. So here's one way to list them. 0, 1, 2, 3, and so forth, all the way up to n minus 1. And now those are the only ones. As we said, the representatives 0, 1, 2, 3 are not unique. I could have also started with 1, 2, 3, and so forth, all the way up to n. Well, in lots of other ways. Okay, let's head to the proof. Number 1, of course, is sort of two proofs, one to the right, one to the left. So let's head to the right first. Here we're assuming A, the congruence class of A, is equal to B. So by definition, of course, B is an element of the congruence class of B because it differs by a multiple of n. And since that's equal to A, that means that B is an A, which means that simply B is congruent to A, mod n. So just by definition, we get that. For the reverse direct, commonly when you want to show two sets are equal, which is the statement congruence class of A is equal to congruence class of B, you show mutual containment. So let's show that A is contained in B first of all. So start with an arbitrary element in the congruence class of A, call it C. By definition, this says that C has to be congruent to A, mod n. But A is congruent to B by hypothesis, so by transitivity, C is congruent to B, and therefore C is an element of B. And that shows that A, the congruence class of A, is contained in the congruence class of B. The reverse inclusion is similar, so we won't write that one. All right, part 2, we want to show that congruence classes are identical or disjoint. So suppose we're in the case where they're not disjoint. This means the intersection of A and B is non-empty. We want to show this implies that, in fact, those two sets are equal. And that'll finish up too if we establish that. So start with an any element, we'll call it C, that's in the intersection of those two. We can do that since the intersection's non-empty. Then C is in both of them, so C is congruent to A, and C is congruent to B mod n. And in turn, this implies that A is congruent to B mod n, which, as we've already seen, means that A is equal to B. And we're done with part 2. Okay, let's go to 3. First of all, any integer k is obviously in the congruence class of k. So that means if I union all the congruence classes, I certainly get everything, since k was arbitrary. All right, next, we need to know that it's a disjoint union, but that's part 2. Each congruence class is the one we already had, or it's completely disjoint. So part 4. Well, if A is equal to nq plus r, then of course this says that A is congruent to r mod n. And again, by part 1, of course, that says that A is equal to r, and we're done. Part 5, by the division algorithm, any A is equivalent to its remainder after division by n. And the remainder is between 0 and n minus 1. So that means our list of 0, 1, 2, 3, all the way up to n minus 1 by part 4 is listing every possible congruence class. And then we need to show that none of these are equal. And that's simply because the difference between any representative that we have here is less than n, so they can't be divisible by n. All right, so that'll be the end of that proof there. All right, one final definition will be done with this section. The collection, or the set of all congruence classes, is itself given a name, and it's called Z mod n. And it's important to remember that Z mod n is itself a set of sets. And you can write it this way. And of course, it's a finite set. In fact, there are only n elements in Z mod n. All right, that's the end of 2.2.